Okay, so today we're going to continue our tutorial. Um, but actually, the first thing we're going to do is going to be in whiteboard, and we're going to actually look at truth tables. And so this is a pretty essential part of any programming. It'll be very useful even in data analysis when you're creating functions and handling data. So this is um, truth tables have to do with if logic and being able to filter out via Booleans true and false. So I think this is pretty intuitive for most folks. Let's see, if I have two conditions, A and B, and we have true, 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 false, false, true, and false, false. There's a couple different sort of notations to learn here. In R, the AND operator is an X, oh, sorry, not, is an ampersand. The OR operator is the straight vertical line, and the NOT operator is an exclamation point. So what does this mean? So for column A, if I were to say not A, then it just becomes the opposite of whatever your condition is. So not A, true would just be false, true would be false, and then the two falses would be true. And then you can use the and/or logic as well. So if I had A and B, okay, who wants to chime in here and help me out? So if two things, if it's true and true, then is it true or false?
True.
True, great. And then if it's true and false, is it true or false?
False.
False, that's right. So I think the best way you can think about this is sort of common examples. So I might ask, are you wearing like a shirt and a pants today? And if they're both true, right, then it's true. And that would be different if I were asking you, are you wearing a shirt or pants today? And if it's or, then it only cares about if one of those is true. So if any of them are true, then it's going to be true. So in this case, true for A and B, true, true is true, true, false is false, false, true is false, false, false is false. And if it was A or B, it would be true, 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 false. And so these types of truth tables are nice little exercises. You know, you could extend these to be more complicated. And actually, you know, we'll have a sort of truth table on the first assignment. But you can do, you know, things like not A, or you know, A and B, stuff like this. So they can get pretty complex, but if you work out the base logic, you can go sort of step by step. right here, if I were to, you could break this part down into A and B here. Let me actually change the color. So A and B here, and the not A here. So then you would have an OR of these two conditions. So you could just follow this and say for the ORs, right, as long as one thing is true, so this would be true, false, true, true. Yeah, and so this logic is particularly helpful in working through if conditions, which we can now sort of take a look at in the code itself.
Alan, can I ask a quick question?
Yes.
So basically the question that the logic test you were applying back there when you were drafting up that whiteboard table was like, is that true? So like when it was A and B, you were asking like A and B like is equal to true. And
that's right.
okay.
So
Cool.
A itself and B itself are just giving the Boolean condition of true or false, and I can combine those. So so actually I can sort of represent that in our do I have my screen being shared right now?
Yep.
Yeah, okay, great. Let me just pull this up as well. Okay, great. So if A is true and B is, let's say, false, I've executed both of those, and now I have true and false here. I can look at A and B versus A or B, and I can run these conditions, right? And so the and is false, and the or is true. Does that make sense? Okay. And so what are some sort of applications of some of this logic? So you can formulate sort of interesting if statements, but we'll start sort of basic for now. Let's assign this value x is equal to 10, and I can do an if statement. If x is less than 1, then print first. So this is a typical if statement that you would see, same type of logic that you would see in other programming languages like Python. So the whole idea is it checks this condition and whether it's true or false. And in fact, you could just put true or false here, and that would qualify as your condition. And if the condition is true, then it will enter into these curly braces and execute whatever commands are inside here. So in this case, I'm asking it to print first. And this follows, I think, sort of common logic. You can check else if, which means that otherwise, if you didn't fall into the first condition, it'll check the second condition. And you can also have a third condition, else, which would apply its logic to everything else as long as you didn't fall into the first two conditions. So if I were to run this code, what would happen?
It would
Yeah,
print third.
Yeah, that's right, exactly. So it would print third. Because it checked the first condition, x is not less than 1, and therefore it moves to the next check. X is not less than 2, and therefore it goes to the last one. Else covers all other conditions. But so because it's comprehensive, as long as it doesn't fall under the first two, it's always going to print the other ones. If, however, I added a condition like this, then nothing would happen because it doesn't meet the criteria of any of these. Let's try something like, so let me see, 15 and 20. So in this case, it prints first, but not second, right? Because it only checks for one condition and stops afterwards. And again, you can think of this, I think, in my opinion, the best way to think of this is sort of just formulating this in English. If you're making these sort of if statements, right, then the first condition that gets applied halts all the future conditions. And then in terms of the truth table logic that I was talking about before, you could apply that here. So if x is less than 1 or x is greater than 9, in the first condition, x is less than 1, that would be false. But in the second condition, it's true. And because you're in an or statement, then it ends up being true. And so in this case, it'll print first. But if I do an and statement, it'll go to the second condition because a true and a false will be false. So this is pretty helpful for like filtering data. So if you have a data set, in fact, I could do a quick sort of practical example of that. I think it's data like this. Yeah. So R has default data sets, and I know we haven't talked about data frames yet. We'll get to the filtering part in a little bit, but let me just pull this up here. Actually, oh, this is not what I want. It's empty cars. So here, and we'll go into a little bit more detail about this in a little bit, but I could actually say filter out cars that are, above a certain MPG and have a certain number of cylinders, right? So I could do something like empty cars where if I want all cars that have a fuel efficiency greater than 22, and I want all the cars with more than 4 cylinders, it'll return nothing because there aren't any cars apparently that are like that. Let's say 20. So then it would return a subset of the full number of cars. And you could do the same thing, but with an or statement. Instead, which will print, oh, hang on, I need a comma here. Which will print a different subset of vehicles than the ones that are that's in the and, right? So this type of tool, and I'll cover more exactly what I did here, but this type of tool is useful for especially purposes like this, where you have multiple conditions. Okay. So moving on, if there are no questions about this. Another powerful tool are for loops. So these are ways where I can pass through a sequence of values to conduct the same operation multiple times on potentially different things. Okay, so what does that mean?
Alan, there's a question.
Oh, yeah, sorry. Why do you add the comma inside there? So that has to do with the functions of data frames. I know this right now, I kind of jumped ahead just to show the capability, but I'm going to talk about that in a little bit. Exactly what's going on with what I did up here. So we'll get there. Yeah, and definitely feel free to type out in chat your questions if you don't feel like speaking into the mic. I will try my best to keep my eye out on that. Okay, so in a for loop, these are again pretty powerful tools. What it does is it walks through this loop, and so this is kind of the easiest example that I can think of, and I'll draw out a sort of different example in a second. But this x in 1 to 10, I can provide sort of any values here, and basically for every value, it's going to take on the set of elements that are in this vector and insert it into the for loop and execute whatever is in here. So let's see. Here it's just printing out x. So as you can see, it's stepped through here 10 times and it changes the value of x every time. So let's do a more complex operation. So this doesn't have to be any it doesn't have to be just like a sequence of numbers. It can be any vector of values. So in fact, I could have this even as strings. So A, B, C, D. And when I print this, oops, it'll print out A, B, C, D, just like that. And it doesn't have to be in any particular order here. It'll go through whatever order you provided it in. So if I do 10, 7, 4, 3, it'll print these numbers out. So let's take a look at if I were to print, say, that number x plus 5, then it's going to essentially conduct this operation through each of these numbers. For something more complicated, I might do something like I'm going to start with a value outside the for loop. And then we're going to see what happens to A as I reassign it. So maybe A will be x divided by 2 plus A. Okay, so in this case, we're doing assignment inside the for loop. And then when I print A, at the end, it's going to give some value. Okay, so 12. So how did I get there? Okay, so when I ran the for loop with C, A, B, C, D, it printed 10. So in a for loop, it actually goes to the global environment, not the local environment. So that probably shouldn't happen. If you, let's see, if you assigned, well, okay, so that part, that's actually a little bit tricky. There is an element of a local environment in a for loop that has to do with the assignment variable. So X is going to get everything that's X inside the for loop will be the local X. If I, let me just do this real quick. If I do something like this for X in 1 to 10, and I print X, what you'll see is that even though I assigned X earlier, what's inside the loop, there is one local variable, which is whatever gets assigned here for your index. So I'm not sure what happened with you, Amy, but you can see that in this particular example, like it printed 1 through 10, even though I assigned 10 here before.
Yeah, I got it. I'm not sure why mine did that. I did have X assigned already in my global environment, but
yeah, so this part is particularly tricky. There is one little bit of local assignment, and that can actually be confusing if your namespace is overlapping. Okay, but so for this particular example here, let's take a look at how we arrive at that final number of 12, right? So if I run this and I type A here, we get to this value. So the way that I like to do this, I like to visualize this, is for each step in the loop, I'm going to call that n. Okay. And let's take a look at what happens as I go through my for loop. Okay. So before I step into my loop, my A is set to 0. In the first step of the loop, n is equal to 1, my X value is going to be assigned to the first value in the loop, which is 10. Okay, so my X tracker is going to be 10. And then for my A tracker, it's going to be 10 divided by 2 plus the previous value of A. So it's going to be 10 divided by 2 plus 0 equals 5. Okay? In the next step, it's 2. My value of X is 7. So it's going to be 7 divided by 2 plus 5. And that's equal to 8.5. In step 3, my X value is 4. So that's 4 divided by 2 plus 8.5 equals 10.5. Wait, is that right? Yeah, that's right. And then the last one is 4. X is 3. And so that's going to be 3 divided by 2 plus 10.5 equals 12. And that was the final answer that we had gotten from the A output. So hopefully that makes sense to everyone. And in fact, I can go in here and you can print out the intermediate steps. And what we should see getting printed are these values 5, 8.5, 10.5, and 12. Oh, wait. Sorry, I have to reset it back to 0. So why did this happen? Why were these different from here? It's actually because I didn't run this code here, which means that when I started the loop, this A value started at 12, which is going to change all the answers. But if I reset it, then we get 5, 8.5, 10.5, and 12.
Hey, Alan, I have a quick question.
Yep.
When you did the 4x in range 1 to 10 there, in R, are those types of ranges always inclusive of the first and last number? Because I know sometimes it can like exclude the last number.
Yeah. So what you're talking about is functionality differences with Python, and actually, I think you're specifically referring to actually version differences between Python 2 and 3, as well as differences for range and X range, right? So in R, it's always inclusive, and again, the tricky thing to remember is that the indexes all start at 1, not at 0. So that'll be something to keep in mind for differences here. Yeah, so when I do 1 to 10, that's gonna, let me clear this. So that will print out 1 through 10. So it's always inclusive.
Thank you.
Yep. Okay, so let's take a look at an example where I'm incorporating both my if statements and my for loops. This is kind of delving into a little bit of stuff that you might learn in like a intro comp sci course, but I think it is helpful to start getting your brains to think about the logic and power behind these particular tools. And there are some things that I'm teaching in the R tutorial that are like good to know in theory, but don't get applied so much. But when it comes to for loops and if statements, yeah, I don't think there's a single sort of coding session that goes by where I don't do this type of stuff. So it's really good to get quite familiar with these tools and being able to understand them and quickly sort of read them. And so we'll have this quick exercise here. What does this function do? And let's see if you guys can figure this out. So the function takes some input x, and then what it does is it checks if x is less than 2. And if x is less than 2, it's going to return false. So I should quickly mention that in a function, whenever it hits return, it's going to end the function and then return whatever it is. So all this following code that I'm about to type out, if it ever enters this if statement, it won't run any of the rest of the stuff. Okay, but there's not going to be an else statement, or I guess everything is going to be in the else for, we're going to call factor in 2 to x minus 1 if, okay, I actually need to teach a new function here. So there's something called modulus. And a modulus operator is kind of like doing a multiplication or a division. So if it's, say, let's see, 7 mod 2, so the mod is done with a %%, then it returns 1, 7 mod 5 returns 2. Okay, so for those who don't know, what is the modulus operator? It is the remainder. So if I do 7 divided by 2, the remainder is 1, and so that returns 1. 7 divided by 5 goes in once and has remainder 2, so it returns 2. So this mod operator is a really powerful thing for condition checking, for if like a number fits into another number. To be honest, I don't use it so much, but it's good for understanding some of these practical exercises. So in this case, it's going to check if x mod factor is equal to 0. So if the number can be divided into, then it's going to return false. Otherwise, if I don't get into this if statement or this if statement, it's going to return true. Okay. So this is not too complex of a function, although me sort of just typing it out in front of you may be challenging to comprehend immediately. I'll just put this out there. Can anyone see immediately what this function does? So let's, no one is speaking up. So let's try a couple examples. So I'm going to put in 3 and it says true. I'm going to put in 4 and it says false. Let's try 20, false. 21, false. 22, also false. 23, true. Okay, some interesting stuff going on. So let's do this example 7, which is true. And let's walk through the function sort of step by step so we can kind of see if we can understand or see if we can figure out what it does. So I'm going to kind of break this down into 2 parts. So the first part here is x less than 2. Okay, so that's going to be a pretty rare case, right? So actually none of the ones that I put in here were less than 2. And in fact, if I were to do like 1, it returns false. But we can figure that out pretty easily, right? I can look at here and just say, is my input less than 2? Okay, false. So that's not the hard part. The hard part is understanding what this stuff does. So let's take a look. We'll do the same kind of procedure. It's a for loop, so I'm going to start with an n. And then the stuff in the for loop is factor. That's the index that I'm going to be stepping through. I do have an x, but the x is fixed, right? So my x is always whatever I put in. So let's go with x equals 7. So this is going to be 7 no matter where my location is. So I'm not even going to bother writing that down. Okay, so in the first step through my factor, it's 1. And let's see. 7 mod factor. My first step through the loop, my factor is 2, right? So it's going from 2 to 6 because x minus 1 is 6, so I'm stepping through this loop. So in fact, I can go ahead and just write that out, 2, 3, 4, 5. And then my factor in step 1 is going to be 2, in step 2 is going to be 3, 4, 5, 6. Okay, and now I need to figure out 7 mod factor. Okay, so 7 mod 2 is 1. Okay, I see in chat someone's figured it out, prime number, right? That's right. And so I'll just sort of finish this example and hopefully people will be able to see. So 7 mod 2 is equal to 1, right? So 7 divided by 2 ends up with remainder 1. And because my condition here is not equal to 0, so then if I were to do this real properly, so does this equal 0? It does not, so that's a false. Here, 7 mod 3 is also 1, so that's also false. And so on and so forth, right? 7 mod 4, false. Mod 5, 2, 1, like this. And so these are all false. So it's going to, let me erase this so we can see. So it never enters this if function because this portion here is never true. And so after testing all the numbers, it's going to say, well, this is not divisible by anything below its number, which indicates that it's a prime number. Okay, so we're going to rename this function is prime.
Alan, I have a question about the factor.
Yep.
So specifically for the bracket that says factor in 2 to x minus 1, and how in the column of the factor you have listed out, it goes from 2 to 3 to 4 to 5. So how I'm interpreting it is that it's still, like every time we go through the loop, it still goes up by 1. But it just goes from 2 to whatever x you put in minus 1. Is that correct?
That's right, exactly.
Okay, great, thanks.
Yep.
Hey, Alan.
Yep.
Why aren't you getting 5 like return values? Like, why isn't each loop printing? Like, I'm not sure if I'm thinking about this right, but wouldn't you only see the return for the last value?
In
on
fact,
how this,
yeah.
like,
so actually, you never enter here because you only enter into the if statement if this thing is true. Does that make sense? So like if I put in 4 instead of 7, then it's gonna hit. Yeah, it's going to hit 2. This part will be true, and then it's going to say, okay, actually, it's not a prime number, right? It's false.
Gotcha.
Yeah. So because you never enter here, it doesn't return anything. Okay. So I'll run this, and this will have this will return exactly as we were expecting, right? So 5 is a prime number, 6 is not a prime number, 7 is a prime number. I can take advantage of like a for loop, for example, and do this many times. For x in 1 to 100, prints is prime x, and actually I can print x and is prime x, and this will tell me for all the numbers 1 through 100 which ones are prime and which ones are not. Okay, something like this. So 67 is not a prime. Oh wait, no, sorry. 67 is a prime. 68 is not a prime. 69 is not a prime. So on and so forth. So this is with pretty simple logic, you can do some pretty neat things. Okay, I see a question from Summer. Is there a way to specify a step size of 2 or 3 in the loop? Yeah, so the loop, again, doesn't care about, it doesn't, I think the reason why that's coming up is we're doing this thing with a colon here, but it can literally be anything that you want. So I could do sequence, if you guys remember from before, this function where I go from equals, let's say 1 to, let's say 20, and I can go in increments of 2. So if I were to just print out this portion right here, then it goes 1, 3, 5, 7, 9, and that's what gets printed in this loop. It can go by 3s, oops, like this. So really, the step size can be anything. It's just whatever you decide to put into this as a vector. Okay. Let's talk a little bit about the big O notation that I referred to before. So if you are paying close attention here, we'll notice that there's something interesting about this function. Do I actually need to check every number between 2 and the number to see if it's prime? This function is inefficient for one particular reason. And who can tell me what that is? Okay, so if I were looking at, if I wanted to check, for example, if 25 were prime, first I'll step through in the same way. I'll see, is 25 divisible by 2? No, it is not. Is it divisible by 3? No, it's not. Is it divisible by 4? No. Is it divisible by 5? So in this case, we would say yes, but okay, maybe 25 was a bad example. Say we'll do 31. So you say 5 is no, 6 is no, 7 is no. It's not divisible by any of those numbers. But if there's any number larger than, say, 8, then you would have already checked the other number, right? Because it would be 8 times 4. So, okay, I see in Greg, I see in the chat, Greg is saying it doesn't need to be divided by a number greater than half the value. Okay, so let's create a new function called isPrimeBetter, and let's modify our, oops, not isBetterPrime, isPrimeBetter, and let's modify this. So in fact, here we would just say x minus 1, and what Greg is saying is divided by 2. So in this case, the for loop gets smaller, right? Because I only need to check half of the numbers. Right, because hopefully that makes sense to everyone. If I go up halfway, then I've already checked the other half of the numbers that would be on the other side of the multiplication. In fact, this is, actually, let me do this. I'm going to put this version called isPrimeGreg due to his suggestion. This is actually not any more efficient than the previous version. Actually, you don't need to check just half the numbers. You only need to check the up to the square root of that number, right? Because once you get there, you've checked the rest of the set of the numbers. So it's not just divide by half. It's divided. It's to the square root of that number. Okay, and so this actually makes a really big difference. When I said that Greg's function, I'm not trying to tease you or anything. We're just going to call it that because that's your suggestion. But actually, that divide by 2, when I say it doesn't make a difference, it doesn't make a difference in the sense of what I was referring to as big O. So the big O notation is a way of essentially figuring out the speed of an algorithm. So say I have a function, x, and this operates with some speed. And when you increase the size, or you're say we're the function is dependent on the size of the input, and so as n goes up, or x in this case, I'll put n instead to be more with the more common notation. As n increases, then the time it takes for the algorithm to compute will scale with some function. Okay, and so the classic example is something like searching through a telephone book. Okay, so if you were given a name in the telephone book and you did what's called a sort of dumb search, a linear search, where you flip page by page, okay, as the size of the telephone book gets larger, then the big O of that telephone book is n. And that means as the size of the problem scales up linearly, then the size of this, or the time that it takes to conduct that operation also scales up linearly. You can search the phone book in a smarter way. I could do it alphabetically and cut it in half, and then cut it in half again, and then cut it in half again. And you would reach your final name, or you would reach the page in which you're looking for with a big O of log n, which means that as the telephone book gets bigger, yes, the search time increases, but with a log n function. And so the way in which we structure our algorithms will have different big O's, referring to the amount of time it takes to execute it. So I want to show that so any like linear modification of n, so if I were to do n divided by 2, we still consider that to be O of n. It has to be an exponential or logarithmic difference, which is why I was saying in Greg's example, it doesn't actually change the computational speed at all. And let's show that empirically with these functions. So I'm gonna run these, and then what I'm gonna do is a pretty simple sort of clocking function. So systime is a function that returns the current time, and you can actually use it to clock specific functions. So what I'm going to do is take a really large prime number. If you take a really large regular number, then it won't actually take any time, because if you look in any of these functions, as soon as it enters the first condition where it returns false, then it's going to halt the execution. And so this actually ends immediately because it just checks 2. and this number is divisible by 2, so it'll end really quickly. But if I put a prime number here, so actually let me just run this real quick. So super fast. But if I put a prime number here, a large prime number, then it's got to go through it has to go through the entire for loop before getting to before returning false, before returning true. So let's take a look at how long this takes for each of our respective functions. Okay, so is prime Greg and is prime better? Okay, I tested this out. It's going to take about 30 seconds to run or so on my other computer, so hopefully this one will be able to keep up. And so what's happening here is that it's running through that for loop, right? And it takes some time to be able to run 1 through whatever this number is, 100 billion about. And as this number increases, my computational time will increase linearly. So if I went to a prime number that had approximately twice as many as this, it would take about 40 seconds to run. Let's take a look at Greg's function. So in this case, we would expect it to run in about 10 seconds, right? So sort of right on the dot there, 10 seconds. And it's the same thing. So even though it's faster, when it scales up, it's scaling linearly. So we're not really saving that much time as this gets bigger, because when you're talking about scaling things up sort of exponentially, it's going to be sort of in the same factor in order of magnitude it takes to run. Let's take a look at is prime better. Bam. Okay, so it's 1, 2, 3, 1,000 times faster. And as this continues to get bigger, if I were to increase this by a factor of 10, right? These two are going to increase by 10x, but this will maybe just double in time, right? And so you can already see with large numbers the benefit here. I can really quickly crash my computer by putting in a large number here, but I'd have a hard time coming up with a prime number large enough to crash my computer using this function. So that's the concept of big O. In practice, I think knowing about this concept and understanding when you're dealing with like large data sets and you're manipulating them, it's always good to keep in mind that like, oh, let's not just throw more sort of computing power at it, right? If I can design my algorithm or whatever I'm doing to be just like slightly smarter, and it's not always the case that you can do this, but oftentimes it is the case that you can. A small change as just adding this right here can make a world of difference in your ability to do some of these calculations and computations. So again, this type of stuff in application is really on a case-by-case basis. So I don't really have any good sort of generalized rules for how to always improve whatever it is that you're doing. But hopefully, at least knowing this concept, you can always turn to this thought process where you're like, okay, is there anything I can do to kind of like help speed up what I'm doing, and not just like think about moving it onto like a more powerful computer with more memory, that kind of thing. Okay.
Alan, I have a basic understanding question.
Yeah.
Could you explain again why switching it to like raising it to the square root works in this case?
Yep. Yeah. Sure. So the whole idea is basically like, let's say I'm going from if I'm in a large for loop, and this is whatever it is. Let's say I'm going to a large number called x. So it's 1, 2, 3, 4, ... all the way down here. So as x gets bigger, then I have to step through this. This should be like a up arrow. So as x gets larger and larger, then I'm stepping through this for loop, and it's linearly taking me a longer time, right? Because I have to go all the way up to x. When I instead go up to root x, then as x goes up, then I only need to go to root x. And so how many steps would I need to go up to, say, 100? In the linear case, I would need 100 steps for x, but in the root x, I would only need 10 steps. So I've reduced it by a factor of 10. If I go up to 1,000,000, then I would need, let's see, I would need 10 to the 6th steps, but I would only need, 1,000 steps here. So now, so in the 100 to 10, that's a 10x decrease. In 1,000,000, that's a 1,000x decrease. And then 1,000, it's 1,000 times faster, right? To do it with this many steps. So by adding the root part here, it's decreasing the number of times I need to go through my for loop, or number of steps in the for loop. Does that make sense?
Yeah, it definitely does. Thank you. And mathematically, you don't lose that. Like,
yeah, mathematically,
you're certain that you would
yeah.
have checked all the possibility that it's a prime number.
Yeah. Oh, okay. I'm seeing a comment. Can I show? Okay, really quick before I do that. Yes. So I'm certain that I don't need to go above 10, right? Because let's say I'm testing the number 101, and I go 1 all the way down. So root 101 is approximately 10. Okay, so if I go all the way, if I check the numbers 1 through 10, then 10, if I go past it, if I go to 11, 11 would be multiplied by 9, right, to get up to about 101.
Okay.
And then
okay,
12 would get multiplied by about, 8 to 9 to get to 101. But I've already checked those numbers here.
Okay, that makes a lot of
so
sense.
yeah, so you don't actually need to check all the numbers, which is why this way is much more efficient. Okay, so can I show?
Thank you.
Yeah, can I show is prime next to is prime better? Yeah. So literally, okay, literally the only difference is this right here. So if I delete this, then it becomes is prime, and then if I include that, then it's is prime better. Okay. So that is testing that out. Okay, so we've covered, let's see, we've covered basic operations and functions, custom functions, and now we've if statements and for loops, and now we've sort of combined all of that into sort of one piece where we're doing operations and if statements and for loops and a custom function. So it's a sort of quick and dirty application of a lot of what we've learned so far. So you know, this honestly, we are going through this pretty quickly. So if this is at all confusing, do try and take some time to try and understand what's going on. I think especially for loops can be oftentimes confusing if you've never seen them. And my recommendation again would be to, you know, go through this like table that I'm drawing step by step, where you walk through the loop one step at a time so that you can understand exactly what's going on. We're gonna pivot a little bit now away from some of the like operational aspects of R to think about some of the how it does structuring, handling data, handling types of data. So this is kind of intro into slightly different concepts in R. So we're going to look at data types. And this will also apply to other like data structures as well, not just data types. And we'll see what that means in just a moment. Okay, this is a number. So this is mainly what we've been working with so far. This is what R refers to as a numeric data type. So if I run this, I have now stored an object called this is a number, and it just returns 1. And I can now do a test to see whether or not it is actually a number. So this is a number. And it is indeed a numeric value. And I can test this for other types of things, and it will return false if it's not a number, right? So this is a character, what a lot of other programming languages refers to as a string. Before we get there, I'm going to show a different type of number. So this one is fairly unusual. I can't actually ever recall using this practically, but it's there, so might as well learn about it. This is an integer. So an integer, so hopefully everyone knows what an integer is, just like a round number, no decimal points. And to specifically specify it as an integer, you have this L here. And so I can also check this is dot integer, this is an integer, and we should see, boom, okay, makes sense. So now what do you guys think? Is this numeric? It is. So integers are also numeric, but even though this is specified as just 1, if I see whether the number is an integer, it is not. Okay, so all integers are numeric, but not all numerics are integers. Okay, and again, I very rarely, if ever, use that function. So just a heads up, it's probably pretty uncommon to be using something like that. However, this one is much more common to use strings. And the thing that we check here is character. And if I do this, it will return true. And numbers are not characters, so is.character 1 false. But if I put quotes around it, true. And so anytime you put quotes around something, it specifies that it is a character. And so if I put quotes around a number, it will not be numeric. Yeah, sorry. So in this question, what does L do? Yeah, that's right. So it will indicate if the number is an integer. That's exactly right. So you would add an L after the number to say that it's an integer. You can't like you can't do something like this because there's decimal points. And it won't round it, it will just assign it as a numeric value instead of being an integer.
But is it 1 inherently an integer?
No, it is not. So that's what I was typing up here. So actually, we could just test that directly. Is.integer 1 false. It has to be explicitly denoted with the L to be an integer. Okay. We actually have already used a different type of data type, and that is a Boolean, which R refers to as a logical. So true and false are unique things in R. And that's just like a 0 or 1 value. Note that you do have to say in all caps true or false. It can't be like, it can't be lowercase. That won't work. Although, actually I can't remember. Yeah, that's right. So the one thing that does actually work is you can abbreviate it with T and F. So both of those will be true and false. And I can test this with is logical. This is a logical, and that will return true. And so these are all additional sort of filters that are extremely useful for getting into these logicals, and oftentimes you'll be using stuff like this in like if statements or filter statements to get at specific values. So these will be good to be pretty familiar with, except the is integer and this one that I'm about to show, which I've definitely never used. So this is an imaginary number. And you can test whether it's complex with is.complex. Yeah, and this one, along with integer, are really rare, at least in R fields. It'd be pretty unusual to be doing complex, using complex numbers for like data analysis. You can switch between data types in certain sort of instances. So suppose I had a character y, 1, 2, 3. So we know that this is a character and not a number, right? As numeric, y, false. Oh, oops, I did not mean to do that. Is numeric. So that's false. And then is.character y is true. But I can transform that into a number with the operation as numeric. And then if I check again, is it a character? No. Is it a number? Yes. Oops. Is it a number? Yes. And you can change it back to a character, like so. Okay, what happens if I try to do as numeric to a string that doesn't have any numbers? It'll just do NA. Okay. We have already talked about vectors, but there is an aspect of vectors that we haven't discussed. So this is a vector of numbers 1 through 4. And actually, I can test whether the vector contains numbers versus other data types. And it tells me it's true. Great. So that's pretty much what we expect, right? Because all the entries in the vector are numbers. Another thing that we haven't discussed is that I can actually reference specific values in the vector. So this is really important for understanding how indexing works. So the way you do it is with this square bracket. And so any number that I put in here is going to return the position of the elements in the vector. So if I put 1 here, it's going to return 1 because 1 is the first instance. It'll actually be better if I show this with the next example. So I'll come back to this in a second, so that'll be easier to understand. So vector 2, we're going to call this A, B, C, D. So this is a vector of characters. And if I do is.numeric vector 2, it's going to return false, as we expect, right? Because these are characters. And if I do is character vector 2, it's true. Great. That's what we want, right? These are all characters inside the vector. And so false for numeric, true for character. Okay, so same thing as I was saying before with the vector 2. If I want to return 3, or if I want to return C, the letter C, which is in the 3rd position, then I can just put 3 here. Oops. And it's going to return the letter C. You can do multiple things. I can do entries 2 through 4, which is going to return B, C, and D. I can return it via, if I do a vector of values here, 1 and 4, which is the first and last one, then I can do A and D. I can return something like this, 1 comma length of vector 2. So this is a handy little trick sometimes if you have like a dynamic, if the vector size or the table size is changing dynamically, you could do this instead, or length or n row. So the length of vector 2 is 4, so it's going to return the same thing as here, A, D. But if I increase this by 1 and add E into here, well, entries 1 through 4 are going to stay the same, 1 and D, but 1 and length vector 2 is saying return 1 and the last entry, essentially. So it'll return A and E. Okay, I see question. When typing a list of characters, is there a shortcut to put quote marks around all elements without typing each one? Let's see. Kind of. There are ways to do that, although yeah, I can think of some ways to do that, but actually I'm not gonna say, because I think that is actually not good practice. If I'm thinking of what you're if I'm thinking in the way that you're describing. So that's like, that would be something like, and then some function to add quotes, right? So it would be something here. So the
Alan,
reason, yeah, okay, yeah.
Keyboard shortcut.
You mean like that?
Yeah, like, do I literally need to type quote A, quote, comma, quote B, quote, comma, or is there a shortcut to doing that with a big list of strings?
Actually, I'm not sure. So I think I don't think so, because I think if I do the quotes here, it's gonna, yeah, quote the entire thing. So the shortcut to like add quotes to something you've already typed is to just press the quotation mark, and then it'll wrap it into something. But if you have like many items, I don't think you can do that. So there is actually a way that I could do something like this and then wrap each of these individually after I've typed it out, not like as a shortcut, but as like a functional type thing. But you really shouldn't do something like that, because you are, when you have characters that aren't quoted, then they're referred to as objects, and you're confusing the space between strings and objects, and that's typically pretty, like, that's not a good practice to do. But in reference to what you're talking about, which is, I think you just type A, B, C, D, E, and then have some kind of like keyboard shortcut to add quotes around the ones that are delimited by comma. I don't know of any way to do that. I've always typed it out. So yeah, sorry, I don't know of a way to do that. Okay, so moving on, let's take a look at a mixed example. So vector 3, we're going to do as 1, 2, and then A and B. Okay, so this is pretty interesting. We have a mixture of numbers and characters. So usually I would ask in class to like raise hands. So just have it in your mind what you think is going to happen, and then we're going to see if it is what you expect. Okay, so I'm going to do is numeric, and think about if you think it's going to be true and false. It's false. And then if I'm going to do is character, think about if it's going to be true and false, and it's true. Okay, so what the heck happened here? How come when we put numbers in, it's not numbers and it's characters, but then it's, so you might think, for example, that it has to have the presence of all of them, but then why is character true, but is numeric false? So here's the other thing that we didn't talk about with vectors. So vectors can only contain one data type, okay? You can't mix characters and integers and numeric and complex and what's the other one? And logicals. You can only have one of any of those in there. And once you start mixing them, it's just going to assign it to the most generic one. And so if I have numbers and integers, it's just going to make them all numbers. If I have numbers and characters, it's just going to make them all characters. So if I take a look at vector 1 versus vector 2, in the printout, what you'll notice the difference between numbers and characters is in the console, it has these quotes around characters, but no quotes around the numbers. So when I type in vector 3, you'll notice that it has transformed my 1 and 2 into characters. So even if I do is numeric, the first element of vector 3, which is 1, it's going to return false. Even though we had originally said that that was a number, it converts everything into a character by default once you have any mixing occurring. Okay, so a question. A number can be a character, but a character can't be a number. So I guess that's kind of one way to think about it, but you can't. But a character isn't actually like yeah, a character isn't actually a number, but yeah, you can represent a number as a character, but you can't represent a character as a number. And that's why it'll do it to the more generalized one. Yeah, so hopefully that makes sense. Let's continue on. So you can have more than one dimension of a vector, and a two-dimensional vector is what we call a matrix. And so I can show what that looks like. Matrix is something like this: 1, 2, 3, 4. And I'm going to just explicitly specify 2 rows and 2 columns. So this is a function similar to C. These are the entries into the matrix, and then these are the dimensions of the matrix: number of rows, number of columns. And when I hit enter and I look at matrix 1, it'll look like this. So it's going to fill out, notice, by columns and then by rows. So it goes down and then across. So 1, 2, 3, 4. And the rules for a matrix follow the same rules as a vector. And so if I do is numeric, it'll return true because I've only inputted numeric values. But if I put in character values, then it's going to return as character. So remember, in the vector example, I can return specific entries, but with this square bracket, and I can do the same with the matrix. Okay, so let's say I wanted to return the number 3. So that would be in row 1, column 2. So same thing as the vector, except now I'm specifying the dimensions of where I'm looking. And so this is going to return 3. So you can go actually in more dimensions, but for matrices and for tables and data frames, which is the most common, you return just these 2 numbers. And because it's so common, you have to make sure to remember the order. It's always row column, RC, row column. This is one of the things that people get confused the most. So I'll just keep saying it. I use the mnemonic device RC cola. So that's going to be your way that you don't forget. Okay, it's always row column. You can always think of RC cola so that you don't forget. Okay, so that's for matrix. And you might ask, well, can you have more than a two-dimensional vector? Yes, so you can have an n-dimensional vector or n-dimensional matrix. And it's basically the same format, and we call that an array. So to show what that looks like, so 1 through 8 now, and I'm going to do dimensions are 2 by 2 by 2. Okay, so we've gone from our vector of one dimension, just a vector of numbers, into a 2 by 2 matrix, into a 2 by 2 by 2, which will look something like this. Okay, so it looks like two flattened matrices, and if you can kind of envision this in like a cube, right? It's like the first layer of the cube is the first 2 by 2, and the second layer of the cube is the next 2 by 2. And really, you can do this in as many dimensions as you want. And the reference point, you can always kind of like look at how these are arranged to see. So if I want to return the number 6, then it would be row 2, column 1 of the second slice, right? And so this would be array 1 of 2, 1, 2, and that's going to return the number 6. Can I give an example of where we would be using arrays? Not really. I don't use arrays that often, but I just want to be able to quickly teach about this so that you know what it is. Arrays, I think, are kind of less common to use. And I'm saying that not because this isn't a type of structure that I use. In fact, I'm about to show a more flexible type of thing. And the reason I don't use the array is because I use the more flexible type of thing more often. And so, yeah, so one of the functionality of matrices and arrays are really geared towards doing sort of like matrix-based numeric operations. But when we talk about like data and object handling, it's not so often that you'll be needing a structure like this. More often you'll be using a structure that needs to be slightly more flexible. And you might be thinking to yourself, well, one of the big drawbacks of like doing vectors or matrices or arrays is that unfortunately I can only have one kind of data type. But what if I want an object that can store lots of different sort of data and data type? Well, there actually is something in R for that, right? And so this is called a list. So list is like the giant bucket that can just take anything into it. And so it can store any object, any combination of objects, and they don't have to be the same data type because every entry in the list is kept as like a separate sort of object. So let's show what that means. So vector 1, vector 2, vector 3. I'm just gonna go ahead and throw in all of the examples that I just made into one giant list. Okay. So my list contains 5 objects, and each of those objects is just whatever whatever I defined before, right? So if I wanted to look at vector 1, then I can do that. The first entry of list 1 is this thing, vector 1, which is 1, 2, 3, 4. I can look at the second entry, which is I believe it's the ABCD. Oops, not list 2, list 1, entry 2, ABCDE. And in fact, you can explicitly see that wait a minute. Hang on, why did that happen? Oh, yeah, okay. Okay, let me come back to this in a second. I'll just tell you that it is indeed storing data of different types, and that it preserves the fact that vector 1 is numbers and vector 2 is a character, and vector 3 is a character. There's something that I'll get back to about the functionality of a list. The dimensions of a list is you can get with dim or with length, depending on how your list is structured. If it's 2D, then oops, it's because list 1. If it's 2-dimensional, then the list isn't going to have any dimensions. But dimensions actually is referring to any, it can actually measure not just lists, right? So for array, the number of dimensions, right, looks like this. It's a 2 by 2 by 2. So it'll tell you along all the sort of directions how many, how long or how many elements there are. Okay, so if I want to refer to a specific item, generally, so this works, but for a list, you should use double braces. So the list elements, the way that I'm sort of able to properly distinguish between the indexes of the list versus the indexes of the objects inside is this notation refers to the elemental components of the list. And so this will return specifically the first element of that list. I realized that what I had typed in before with 1 square bracket, it works, but it's returning something that I think is a little bit counterintuitive. So forget about the one with the single square braces. When you're working with lists and you want to get into a specific item, you should use the double square bracket. So I can go into a specific object and return, and it would be the same as though I were just operating on that object. So if I wanted to look at this array and do what I had done before, where I'm returning this element in the array, the second row, first column, second slice of that array, you could do that in this list, right, by going here, which is the equivalent of just saying array 1, and then I'll just add on 2, 1, 2, and that's going to return 6 in the same way. So here, this is like a multi-dimensional type of thing because it can handle many objects, and this is much more common to use because we could be storing many different types of things in here. Okay. Barring any questions, which I don't see, let's move on. So these are most of the generic data structures, and vectors are going to be really common. Matrices and arrays are going to be less common to use. There may be some instances in which you draw upon them, but lists are are pretty common as well. Okay. The last one that I'm leaving, that I'm going to talk about, is definitely the most confusing. I personally hate this one, but it is useful and it is really common, unfortunately. I would say, so do pay attention here, because I think probably 95% of the errors that you're going to run into when you're starting to learn about R is right here. Okay, so the last data structure is actually called a factor. There's actually a misconception that factors are in the upper category. So this stuff up here are data types, and all this stuff that I've been talking about here are data structures. Part of the reason why this starts to get confusing is because most people consider factors to be a data type and not a data structure. But in reality, it's actually considered a data structure, even though it operates principally and application-wise under like a data type, or what we would consider as a data type. Okay, so this is a factor. Part of the reason why this gets confusing is because when you like load data sets, oftentimes characters get loaded in as factors and not as characters. And so that's something really important to keep in mind, because I guarantee you, you will at some point run into some kind of factor errors. Okay, so what is a factor? A factor looks something like this. It looks a lot like a set of characters, but actually what it is kind of like a set of dummy variables. So essentially each, you have to define what are called levels, which tell R essentially what the allowable objects are in the definition, in what you're sort of defining as a factor. And each one of these values, so I have 4 values here, this is a factor. So each one of those values has actually a corresponding like index number. And the reason, and there are like actual pretty good practical applications for why you would want to do that, right? With a string or with a character, when you do certain types of operations, they can take a really long time, because you're basically operating over a set of values. I'm calling them values, but like especially the alphabet, right, which is much larger and more difficult to sort of handle. Whereas these levels are just doing Boolean values. It's basically doing these shadow values of 0s and 1s for each of the levels, which will make it so that if you think of it that way, then I think some of the intuition behind things that people typically find confusing about factors may be a little bit more clear, because there are some operations that you can do on factors that you can't do on factors that you can do on characters, that don't make a lot of sense why you can't do them. I feel like I'm speaking kind of cryptically, so let's just go into a couple examples to see what this means. So are factors characters? No, they are not characters. So if you do is character, it's false, so that doesn't work. Is it a factor? One would hope so. True. You can look at what are the levels of the factor. So these are the 4 levels that we defined. A factor is this. Number of levels. There are 4 levels. Okay, so let's take a look at a function called order. So this function is meant to order, meant to put things into a specific order. And actually, vector2 was a set of characters, but it's actually telling you in alphabetical order what position like A and B and C and D and E are. So if I were to mix that up, let's see, if I were to redefine vector2 as E, B, C, A, oops, E, and then I run order vector2, it's going to tell you how to, wait a minute, what's going on here? Let's see what it returns. Yeah. Oh, yeah. Okay, so it reorders in the order. So in position 1, you should put the thing that is in position 4, which is A. In position 2, you put the thing that was in position 2, and so on and so forth, right? So the ordering will alphabetically order. If I order a factor, it's going to order it by the order that you define in the levels. So in this case, if I order factor 1, 3, 4, 2, 1, and that's because, let's take a look at factor 1 again. So this is the third, or let's see, no, sorry, I'm getting confused in the same way as the one before. So A should be in position 1. So the third one goes up front. And so this is actually in alphabetical order again, but it doesn't need to be. So I could put this here instead of at the end. And that would affect the way that the order operations happen. And when I order this, 3, 1, 4, 2, so it doesn't return it in alphabetical order. It returns it in levels. Okay, Greg is asking, is this like a categorical in Python? Yes and no. So some aspects of factors make it like a categorical, but there are some weird things about factors that make it slightly different. But I would say for most purposes, yes, it'll operate as a categorical. Okay. So one of the things to know is that you can, let's say if I look at vector 2, oops, E, B, C, A, D, I can, let's say, add on a value at the end. Let's say I want to add on vector 2 to vector 2. So I'm combining vector 2 and an additional element, and I'm going to say AB. Okay. I can do that. And vector 2 will now be one element longer, and it's got AB at the end. I can also do replacements. So if I want to replace the second element, or B, with, say, BC, that will overwrite element 2 with BC. Cool. So let's see what happens if I try to do string operations on factors. So let's add in to the end of the factor the same thing, AB. And let's go ahead and replace, so factor, let's replace the second element is with something else. Okay, so think carefully about what you think is going to happen here. And now let's take a look. Wait a minute. That was not supposed to work. Okay, hang on. I must have. Okay, wait. I know what happened. Okay, scratch that. So forget this first line for a second. We'll talk about that. Let's do this. So I'm going to replace. I'm going to replace my second entry with BC. And let's take a look at what happened. We got this warning message, and we redefined is into BC, but now it's an NA. And the reason for that is because we didn't specify that as one of the allowable levels of the factor. So it doesn't know what to define it as. Remember, if you think about this as like A is equal to 1, or this is equal to 2, factor is equal to 3, is equal to 4, and now I put in BC, and it's like, well, I don't know what BC is, you didn't tell me, so I'm just going to put NA. So that's what happened here. If you don't have the levels defined for elements in your factor, it's just going to turn it into an NA. I thought that was what was going to happen here when we tried to add something, but I realize now what happened is, remember, when I do a combine function for whatever data that I put into my vector, it goes with the most generalized. It transforms everything into the most generalized thing. And in this case, it's just going to turn everything into characters. And so this actual thing right here is exactly an example of a common mistake that you could see. Say you load in a data frame and you have a column that's actually a factor, and you don't realize it's a factor, and you say, okay, I'm going to replace some value with this, and then maybe I'm going to add on an extra row. Then you're going to get this. You're going to see this NA here, and you're like, wait, I replaced it with a value. Why is this NA? And like, why did this show up, right? It's because of this turning it into an NA in the factor and then transforming it into a character. So these sorts of like mix-ups with factors are common. I mean, I see this time and again with lots of students learning R, and I've made this mistake countless times. So with factors, you have to be extra careful to do certain types of operations. And even one common one that I'll see, for example, is you'll have a column that you'll load it in, and it'll be a column of numbers, but maybe you'll have a mistake, a data entry mistake, where there's like a character in one entry of that column, and so when you load it in, it sees that, and then it loads everything in as a factor, and then you end up trying to do a mathematical operation on the column, and it errors out, and you realize, oh, it's actually it came in as a character, not as a factor, or it came in as a factor, or character, not as a number. And if you change it to a number, everything errors out, because you can't actually do as numeric. You have to change it to a character first and then to a numeric. So there are lots of examples that I could give of places you commonly mess up. So just keep that in mind. Okay, so we're running right to the end of the lecture. So if anyone has any questions, feel free to ask now or type it out in chat. I'll just quickly go over as a summary what we covered today. We finished up some of the operational stuff, right, with if statements, for statements, and then combining it together. And then we talked about data types and data structures. We haven't finished talking about data structures. In fact, next class we'll dive into probably the most useful one, data frames, which is the default way that R handles lots of its data. And we'll talk about how to manipulate data frames, how to filter things, and so on and so forth. And then we'll talk about some other practical tools in R. I'll talk a little bit about more advanced data structures that are coming through packages that I like to use that I think are really handy. We'll talk about plotting. In the previous ones, have talked a little bit about the default R plotting, but now I'm going to skip that and just go straight to ggplot, which really is the more robust way to do plotting, and I think easier to learn. And then lastly, we'll talk about R Markdown, which is actually new to me too. I've never really worked in that environment, but hopefully will be useful for you guys in the future. Okay, let's see. I do see one question before we end. So do the different types of data types have implications for the amount of memory that is used? Yes, most definitely. So numbers is the most efficient, characters are the least efficient. Factors, depending on the number of different levels, will be more efficient than characters. But as is the case for basically all programming languages, yeah, memory efficiency can play a role. If you are starting to use data sets where you're running up against like the memory constraints of your computer or your server, you definitely need to think about how to handle this. It's not something that we talk about so much in this class, other than I'll point out that it is possible to do things like indexing, making relational tables, but once you're getting to that, to a less manageable sort of memory size, you either need to make your data frames, data tables more efficient, or you need to start using databases. Oh, okay, so another question, how can we store factors as characters? Yeah, so I guess I didn't mention that. So the factor one, let me go back to here. It's pretty simple. All you have to do is as character factor one, and it transforms it into a character. So I'll make a note of that, as dot character to transform factor to character. Great. Okay. Well, that concludes our lecture. I know we're slightly over time, and I've been informed actually that we're supposed to start at 10, not 10:10. So I will progressively start a little bit earlier. Maybe we'll start at like 10:05 in between, so that we'll give enough time for people who didn't hear that to join in. But I will try and start a little on the earlier side to be in accordance with the proper schedule. Okay, great. Thank you, everyone. And I will, I guess, virtually see you all on Tuesday.
Thanks, Alan.
Thanks, Alan.
Bye.